everyone. Welcome to the last talk of the workshop. Thank you all for being here. Our next speaker is Angelina Lee. Angelina works on runtime systems, compilers, etc. for parallel systems. She is interested in making parallel programming easy for the masses.
I have time.
All right. She works a lot with, she does some theory herself, and then she works a lot with theoreticians and applies our ideas to systems. So she's going to tell us a little bit about how that works out for her.
Yeah. Okay. Thank you for the introduction. My name is Angelina. I'm from Washington University, same institute as Kunal. Okay. So when I got invited, basically it's under this premise. Okay. I think the organizer really want to intersperse some talks that covers the nature of algorithmic research on computing system, because this workshop is meant to bring system and theorists together, right? Okay, I'm like, sure, I can do that. I'll be happy to do that. And then I got this email from Kirk. So I'll be fair, Kirk said this, okay, but I'm putting Kunal also on the slide because I'm pretty sure Kunal put me up to it. We're looking for a talk that addresses the following issue, okay? And this is direct quote from the email. Explain to systems researcher what algorithms researcher reasonably can and cannot contribute to system research. I thought about it. It's like, well, isn't that kind of context specific? Can I really reasonably say anything general about that? Or you can explain, particularly to younger algorithms researchers, how to do system-oriented algorithmic research the right way. And I was like, is there a right way? Am I doing it the right way? I'm not sure. Explain how systems researcher and algorithms researcher can best collaborate. I'm like, okay, I collaborated with some people. But as the day gets closer and I think more about this, and I take my task very seriously, okay? I started to really stress out. I'm like, I don't know if I can spend an hour covering these topics and actually give people the right answer. So, and then the light bulb came up. Okay, so in research, when you ask a question, and after thinking about it, you decide you don't like the question, what do? You change the question. That's right. So, this is what I'm actually going to talk about. I think it's in the right spirit, even though it's not directly addressing the question raised by Kirk, okay? So I'm gonna talk about what interesting system plus algorithm research looks like from a system researcher's perspective. I know I do a little bit system, and all my papers have some system and some theory. I guess I kind of consider myself a system researcher because the kind of question that I'm interested in typically is in the realm of system software. And in particular, I really like working with system software and provide support for parallel programming. And I focus a lot on multi-core hardware, although that may be changing, we'll see. And so specifically, a lot of stuff I do basically is within this layer where we call concurrency platform. It's a software layer that between the operating system, run on top of the operating system, support user application, and they provide a linguistic interface for you to specify the parallelism of your computation. And then there's a compiler and runtime that compile the application down to something that the operating system hardware understand. And occasionally dabble a little bit in tool and operating system. Not a hardware person. Okay, so that's about me. And in my humble opinion, okay, again, this is just my point of view. Interesting system and algorithm research starts with a problem with a practical system implication, okay? It explores the solution space guided by theory and informed by system. And then finally, hopefully, ends with a solution that provides good theoretical guarantees and is practical, meaning it can be implemented efficiently, okay? And I'm going to use two of my own examples to illustrate what I mean. The first one, the cactus stack problem. Okay, so as I mentioned, I work in concurrency platform, and this is sort of generally the language model I work with. Here, let's just say we're gonna write a Fibonacci program in a very bad exponential time algorithm. I understand it's bad, but it's very nice to illustrate for what the language can do. Here, say I just want to compute fib of n, and I'm going to just compute that by computing fib n minus 1 and fib n minus 2, and then combine the result together. This code can run in parallel easily because these two tasks are independent, right? So in Silk, the way you would write this code is you spawn the function, and basically the name child function may execute in parallel with the continuation of the parent. The continuation of the parent function being the rest of the statement after the spawn. In this case, fib n minus 2, okay? And then there's a corresponding statement sync that basically says the control cannot pass this point until all previous spawn children within this function have returned. Okay, that's it. Very simple. 2 keywords. These keywords, note though, they denote the logical parallelism of the computation. And then there's an underlying scheduler that help you automate things like scheduling and synchronization that in a way that satisfy what the parallelism specified by the application is, okay? So when I say logical parallelism, right, it doesn't mean literally when I spawn a new persistent thread that the operating system sees gets created and execute this. No, it's just there's a pool of threads, and then the computation gets mapped onto those threads by the scheduler. Okay, so that's the programming model. Now, with this programming model, how do we schedule it? Well, we use work stealing. Okay, how many of you have seen work stealing? Okay, many of you. So as a theoretician, right, what you do is, okay, we're going to model the computation as a DAG. We have nodes. Whenever you spawn, that means there are 2 outgoing edges because that denote dependencies. And then they create one node that for the spawn function, another node for the continuation, and so on and so forth. And then when you sync, it joins together. And then you talk about things like, well, when a worker executes one node, what happened if it enabled 2 nodes or enable 1 node, etc. Okay, don't read this. Because as a system person, this is not how I talk about work stealing. How do I talk about work stealing? This is how I talk about work stealing. There are no notes, okay? There are no notes and DAGs. I mean, don't get me wrong, I love the model. It's simplistic, it's very elegant, it allows you to do various analysis. But when I go to a system conference, when I present to system people, if I do this, I'm just gonna lose them. This is what I talk about. So in practice, how do you actually translate what you schedule, where you think in terms of executing node and such, onto a real runtime system? Well, so we do have the notion of DEC, the double-ended queue, but they contain function frames. Okay, so whenever you have functions that's being executed, the DEC keep track of them. And so in particular here, I'm drawing P, indicating, that's the cores. So we have like worker threads representing like being surrogate of these cores. And each worker have its own work deck, keeping track of the work that they have. Whenever a worker makes a function call, okay, well, we need to keep track that. It pushes a frame corresponding to that function call onto its own deck. And here I'm denoting spawn call being this function is called, this function has been spawned, okay? And that will become important later on. Whenever you spawn, you do the same thing. Okay, this frame spawns, so I push onto the deck and it says it's spawned. And then obviously everybody do that simultaneously on their own deck, doing their own function. Whenever you return, you pop up the function that you're returning from, okay? So far, so good. Now, this is the part where work stealing comes in. Whenever a worker runs out of work, see there's nothing in his deck. It tried to steal, basically, take work from other worker. When a worker runs out of work, it turns into a thief and steal from the top of a random victim's deck. So in this case, say it randomly chooses the blue worker and then takes it. Okay, so just make sure you're paying attention so far. Can anyone tell me why, instead of taking the top frame, I'm taking the top 2 frame?
They need to sync, right?
What do you mean?
Well, if it was this Fibonacci one, right? You had the Fibonacci one, right? You spawned, and then you made a recursive call, right? So
yes.
Those are the 2 things that need to sync.
That's right.
So I would think it's better to put them, keep them together.
Okay, so
That's interesting but wrong, you're going to say.
Thank you. Okay, so good. But the way you said it makes me realize there's something I did not make it clear to you. Okay, what I did make it clear to you is that notice when I call, I push something. When I spawn, I push something. And these frames, actually, by looking at just the way I execute, these are actually, this is the parent of this child, this is the parent of this child, right? As we're executing, so in this case, this function got spawned, and then it made a call, which is this frame. And so what's in the deck actually has this, parent-child relationship. The top one would be the oldest one that the worker owns, and the bottom would be the youngest one.
So
Yeah.
it's not clear to me what a call is. Like, if you go back to Fibonacci, I understand what the spawn was, but I don't understand what a call is.
Okay, so I'm just using it to indicate how the function is invoked, right? So there's a very different notion between what it means to spawn a function versus what it means to call a function. Here, fib n minus 1 is spawned. And what that means is that the execution of this function can execute in parallel with the continuation, right? In this case, this function is called, so it cannot execute in parallel with the continuation. Now, in this case, the continuation just sync, but if you imagine there's another function call here, well, that just means you have to wait for fib n minus 2 to finish before you execute the next statement.
So for this example, what would go on your stack is that the spawn would go for the n minus 1, and the call would be for n minus 2.
Well, okay, good. So I guess another thing I did not clarify, when a worker execute spawn of fib n minus 1, say fib 40, right? It actually go and execute fib 40, which means it's going to then spawn fib 39 and then and so on and so forth.
So they will never be on the deck at the same time, because once you push something on the deck, you go ahead and execute it. And then, so everything on the deck is a parent-child relationship. So these two can never be on the deck at the same time. If you push fib n minus 1 on the deck, you immediately go ahead and execute fib n minus 1. When you return from it, then you call fib of n minus 2.
Ah,
Yeah.
Okay.
No, that's not what,
To understand that.
Yes,
Then
that
in
is
a-
how it works.
In an efficient manner,
that's sequential, not
Sorry?
parallel.
you call the spawn one fib n minus 1, you start executing some processor that's going to call other, it's a recursive function, right?
Yeah.
But then the other one, the fib n minus 2, are you going to start it on a different processor?
Ah, good. Okay, so it depends. It depends. And this is where work stealing comes in. So if, say, this worker is executing fib, say, 39, and then, it actually entered the fib 39 function, it's going to spawn fib 38, and then fib 38 is then go spawn fib 30. And so what happened to the continuation of the spawn fib 39, which is called the fib 38? But it doesn't matter. The continuation depends. If this worker eventually hit the base case and then return, and then it's still on this worker's deck, it will just execute it. However, if in the meantime somebody comes in and steal the continuation, then it will get resumed. Right. Okay, so good. So I'm glad this is clarifying, at least I hope for many of you, that the fact is a worker always execute from a DAG perspective, depth first order, right? When you spawn something, you go ahead and execute it. When you call something, you go ahead and execute it. The steal is designed to basically do the load balancing. Okay, the steal steals the continuation of a spawn. If the continuation of a spawn did not get stolen, it will get executed by the original worker. But if it gets stolen, then that gets resumed on a different worker. Are we clear so far? Okay, now I'm getting a little nervous because this is going slower than I thought, but that's okay. Okay, so here, to answer my own original question, why did it steal 2? Well, the reason being that before, remember I said when you spawn something, the continuation is logically in parallel, so that you can execute in parallel. But when you call, that's not the semantic of a call. when you call something, you shouldn't resume the continuation call on a different worker, right? And so in this case, the reason why it's stealing both is because this function is called. So there's really, you can't resume the continuation of this one. The continuation that you can resume would be the continuation of this one, which is this function spawn this function. And so the runtime is basically keeping track of whether a function is spawned versus called, and then steal things in a way that satisfy that semantic, the difference between spawn versus call. Only the continuation of a spawn can be potentially stolen and resumed on a different worker. Okay. Oh, yeah.
Isn't a spawn is always followed immediately by a call?
Not necessarily. You can have, like, for example, if you write matrix multiplication, you divide things into 4 quadrants. There you would do spawn, spawn, spawn. But then you would probably do the call on the last one.
Yeah, but in this example of fib, like, can you get like 2 spawns back to back on the call
You
stack?
can, but it doesn't do much, and it's actually incur more overhead, because if you spawn this one, what happens is immediately you hit a sink. So there's really nothing in the continuation that you can work on anyway. If you put spawn here, yes, the continuation can get stolen and resume on a different worker, but that worker would just immediately hit a sink and be like, okay, I'm done with this until the spawn function
I
returns.
think the question was a little different. So in the Fibonacci one, you never have a spawn after spawn.
Yeah.
In this, right?
Yeah.
But in the call stack, you can have a spawn after spawn, right? Because this fib n minus 1 is a spawn function,
Yeah.
and its child will also be a spawn function, right? In the call stack, remember, it's a parent-child relationship, not this linear relationship. Does that make sense?
This program, that stack, does this represent this particular program, or is it?
Oh, I'm sorry. Yeah, no, not necessarily.
Okay.
I probably should have made that clear.
Okay.
My apologies. Yeah, no. The stack would look different.
Okay.
Yeah, it would see spawn, 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 and sometimes, yeah. Okay. Okay, so good. Well, so in Silk, we actually implement this scheduler. And this scheduler, well, we like this scheduler a lot. Why? Because it provides theoretically good guarantee, okay? In particular, a few parameters. If we call TP the execution time on P processor, so if you use like 16 processor, P will be 16. Then T1 basically denote the work. In system term, we characterize as how long does it take for your parallel program to run on a single core? A theorist would say, what's the total number of nodes in my DAG? T infinity is the span. Again, in system term, it would be like, how long does it take to execute your program, assuming you have infinitely many number of processors, right? So every time you have parallelism, you can spawn it up to a different worker. In theory term, if you think in terms of DAG, it would be, what is the longest path in your DAG, the length of the longest path? Now, the amount of parallelism you have in your computation is basically T1 divided by T infinity. Okay, you can think of it as how many units of work you can do per step along the critical path. And then we also care about space bound. SP is the amount of stack space used when you run on P processor. S1 is the amount of stack space that you get when you run on just one worker, or the serial counterpart. So using a work stealing scheduler, it provides the following guarantee, where you can get a time bound of TP equal to T1 over P plus some constant, T infinity, okay? And basically, what this tells you is that, well, if your application has ample parallelism, meaning the P, number of core you use, is much smaller than the amount of parallelism you have in your computation, then you can observe linear speedup. And then, it's bounded space. Basically, if you execute on P processor, you use, basically linear to the number of cores you are using, amount of space. Okay. Now, so what's the problem? The problem is that with the way that I just described to you, well, I haven't get into detail, but this scheduler by default does not interoperate with legacy binary. And when I say legacy binary, what I mean is that sequential code that compiled earlier, okay? Not by the platform. Okay, so why? Well, again, when we talk about program execution, we think about stacks. Here, when we say, when you have an execution of a serial language, you can view that as a serial walkup in the invocation tree. So what do I mean by that? Say I have a function A calls B, and then calls C, and C calls D and E. Then, basically, throughout the execution, when A is executing, you have the view of A on the stack. When B is executing, you have the view of B and A on the stack. When C is executing, you have C and A, and so on and so forth, okay? But basically, this happens serially. So you will never, at any given point where B and C need to exist simultaneously, right? Whenever C cannot happen until B return. So when B return, you pop up the stack frame of B, and then you invoke C, and then you push on the stack frame of C, and so on and so forth, okay? This is the view of the stack at any given point for a given function during the execution. Furthermore, when you talk about languages, you also need to think about what baseline language you have. So Silk uses C, which contains pointers. Well, the rule with pointer is that a parent can pass pointer of its stack variable down to its children, but not the other way around. Makes sense, right? A pointer on the stack being just an address on the stack, you can pass it down to your child, and your child should be able to see that memory location appropriately with the right value. But of course, when B returns, it pops off its stack, so it cannot pass its stack variable to A. Now, a cactus stack, which is what we use in parallel program, it basically supports multiple stack view in parallel. So here, I have an example where A spawns B and C spawns D and E. Okay, so basically, these are all logical in parallel. Then now, you still want to maintain the illusion that when B is executing, it can see the stack of B and A. When C is executing, C can see the stack of C and A, and so on and so forth. But you need to support all these views simultaneously, right? Because now, B and C are logically in parallel, so B and C could potentially execute in parallel. And so their stack view has to exist simultaneously. And we call that the cactus stack. It's basically an abstraction of providing such stack view for parallel execution. Okay. All right, so how do we implement cactus stack? Well, in existing implementation prior to this work, basically we use what we call a heap-based cactus stack. Whenever you have a function, instead of coming it from the stack, it basically allocates a frame for that function in the heap. And so whenever it spawns something, it allocates frame at non-contiguous memory location in the heap. And then it needs to put in these special little pointers between the parent and the child so that when the child returning, it knows where to return back to, okay? But what that means is that, well, with this strategy, you get the good time and space bound that I mentioned, but it uses what we call the heap linkage, which is this special linkage that the child needs to understand when I return, right? Usually in regular stack frame, you just pop off the function and then you return back to your parent, and your parent is directly above you in memory. But in this heap thing, that's no longer the case, and you need the special linkage to teach the function how to return back to its parent, okay? And the problem with that is it just does not interoperate with legacy serial code. Sure, today you can recompile all your serial function to teach it to use the heap linkage, but then you have to recompile all your code. And I know, like, maybe as a theoretician, you're like, just recompile your code, right? What's the big problem? Well, this is actually a big problem because when Intel purchased Silk Plus, which is basically my advisor, commercialized this technology, they really, really cared about that. Because you can't, in real world, you can't always expect to recompile your code. Sometimes you have code from the third-party binary. They don't want to give you their source code. They want to just give you the binary so you can execute it, right? And in which case, you don't have the original source code. You can't recompile it. but you still want to be able to parallelize it or have it call back to your own parallel function. Okay, so this is the cactus stack problem is how I define it. Basically, how can we have a scheduler that satisfies all three following criteria? Okay, the first one is good performance. Ideally, the scheduler should provide near perfect linear speed up, which the work ceiling does, the classic one, assuming your application with sufficient parallelism. We want to use bounded stack space. Basically, when you run in parallel, the cactus stack abstraction should not consume much more space per worker than does the linear stack during serial execution. Okay, again, which the classic work ceiling does. But then the serial parallel reciprocity in the previous case that we talked about is not satisfied, which says the parallel function should be able to call or spawn legacy or even third-party serial function, and the legacy serial function should be able to call back a parallel function. Okay, you should be able to go back and forth between serial and parallel. Now, and do so simultaneously. And we actually looked at a lot of different strategy that's existing. The bottom line is none of the strategy that we looked at actually satisfy everything. Okay, it seems like either you use the silk-fi strategy, which require you to recompile everything, and you get the good time-bound space-bound, or if you get back the interoperability or the SP reciprocity, as I call it, you lose one of the two. You just cannot get all three simultaneously. Okay. In the interest of time, and the actual commercial product, like TBB or Silk Plus by Intel, they would rather get interoperability back and sacrifice either the time-bound or space-bound. Okay? The Silk Plus is actually from my original, from Silk R, which was the startup that my advisor did. And he's a theorist, so he cared about the time-bound and space-bound more than interoperability. But when he sold the company to Intel, Intel was like, no, we're not doing that. We're just going to sacrifice the space-bound. Okay. And the fundamental limitation, actually, when you look at it, is just once the stack frame is allocated, its position in virtual memory cannot change, okay, because of the use of pointer. And I'm going to skip this example, which is an example showing you how you can give it the square stack space, but if you use one of the strategy that I described. But I'm going to skip that in the interest of time. Okay, so what is our solution? Well, conceptually, this is what we want to do. We're like, hey, great, I know how to support this cactus stack abstraction. We will play with virtual address space. So today, we define this term, thread local memory map region, or TLMN, being a virtual address range in which each thread can map physical memory independently. Okay? So usually, when you create a process, this is like the layout of your memory. You have the stack, you have heap, you have data, code, and then usually everything is just shared among all the threads in the process, right? So given a virtual address, all the threads sees the same physical mapping. But today, we want to create this thing called the TLMM, where in this region, the stack region, each thread can map different physical page. So you see the same virtual address, but it can have potentially different physical mapping underneath. And the idea is that we're going to allocate the stack of each worker in this TLMM region. So how does that help? Well, that helps because now you can actually have a cactus view that's supported by the underlying virtual memory, where, say, if P1, and again, I'm using this example, A spawn B and C, C spawn D and E, worker 1 is executing B, so it maps the physical memory corresponding to A and B in its stack space, whereas P2, if it's executing A, C, D, it can map the same physical memory for A, but then map the rest of the virtual address range with different physical memory that corresponding to the execution of C and D. Right, and you see that in this case, the virtual address for A in all the execution across workers lined up. They're using all the same virtual address. But whatever underneath A could potentially be different physical memory and therefore corresponding to different children functions. And the nice thing about this is, say today if A has a pointer and it passes the pointer down to say C or B, they are going to see the same virtual address. Okay, so great. I'm just gonna illustrate this, right? Again, you use a linear stack in virtual address. P2 comes in and say, I'm going to steal, and I'm going to steal the continuation of A. So when I steal A, I map the physical memory for A into my own virtual address range, and then I just do my usual thing called spawn C. And if I get a pointer from A, I see exactly the right pointer in that virtual address, which is the same thing as BC's, okay? And when I dereference that pointer, it will be the same physical memory, both in P1 and P2. And then you just execute normally. P3 steals C. In this case, again, it maps the stolen prefix, in this case A and C, into its own stack. So into the same virtual address memory with the same underlying physical memory. But then the rest, you can get a different physical memory, and then you can call spawn E. And again, even if you get a pointer from A, it will see the right virtual address that corresponding to the right physical memory. Okay, great. So, but this is not actually the real solution. Does anyone see a problem with this if we were to implement this?
I see quite a lot of questions.
Sure, bring it on. That's totally fine. You should be, yeah.
Like first, what if there are data races?
Okay, sure, okay. Oh, yeah. In this case, we're not concerned with data races. I mean, the pointer could be just a way for you to prevent like parameter proliferation, but the data you pass in could be read-only, right? Okay, but we're not concerned with data race. Yes, you can have data race in this case if they all like say do an increment on X. Yes.
Yeah, so that's not what we are trying to solve, right?
That's right. We're not trying to solve.
Possible in physics?
Good. That's a good question, which I'll get into. So is T amendment possible? Yes, it is, and I will show you how. What's any other issue?
The third problem is that if we are changing the mapping, does it require the stack frame to be larger than 4 kilobytes?
Good. Right. So in this case, oops, I have one more animation that I didn't show. I'm making an unreasonable simplification, right? Assume that we can map with arbitrary granularity. In a real system, that's just not possible. Okay. So, when you build a system, you actually need to work within the real system constraint and consider pesky question like, well, how do we handle the fact that on a real system, we can only map, at the page granularity, which is typically 4K. And then there's always the question of how do we implement TLM in practice? And then lastly, can a work stealing runtime work well if it needs to remap stack at every successful steal, right? Because before, steal is cheap. You just swing a few pointer and then you resume and you're done. In this case, if you steal successfully, you actually have to invoke a system call and then remap multiple pages in your stack range, right? So is that gonna work well? So all these are the system consideration. We're gonna think about the first one. Well, in the first one, let's come back to this example where A spawn B, C spawn D, and E. P1 just execute. P2 steal. In this case, it's going to map the page that A resides on. And so here I'm using the line to denote that's the page granularity. So inevitably, it's going to map a little bit of B in stack space. And it can't just execute C underneath. It's going to corrupt the data for B, right? But in this case, in C, how does it know how big the stack is? Well, it uses stack pointer. So we're going to advance the stack pointer from where it used to be down to a lower address, pretending that A is actually bigger than what it is before we call C. And so in that case, we avoid overwriting the physical memory for B. And then we can resume. Similarly, if we steal C, again, we're going to map.
Question, Angelina.
Yeah.
So when you do that, don't you have to change the code?
No, because the way it does is that this is basically, you only need to do this at every successful steal, right? And remember, we can only steal the continuation of a spawn function. So by definition, if a function, the continuation gets stolen, that function is a silk function, okay, which is managed by the runtime. Yeah. So we don't need to change the serial binary. Okay, now when you still see, again, you map the prefix, again, you have these additional fragmentation, and you advance the stack pointer, and you do the same thing. Okay, so basically, every time you do successful steal, you potentially create a little bit of fragmentation because you need to advance your stack pointer. And that also means the theory has to change, okay? So in particular, now we have this new term, silk depth, which is the maximum number of silk functions that can be nested on the stack during serial execution. Then now the time bound becomes, instead of which used to be a C constant, now C equal to an order of S1 plus D, where S1 is the number of pages used by the serial stack, okay? And the reason being that in work stealing analysis, where the constant comes from, you can roughly think of it as the constant corresponding to the steal overhead. Well, now, every time you have a successful steal, you need to do the page remapping, and then that costs this order S1 plus D term, okay? And furthermore, the space bound, now instead of just S1, you have, again, this plus D term due to the fragmentation. Okay. But what you get back is SP reciprocity. You no longer need to distinguish function types, and parallel serial code can just interoperate nicely. Okay, so hopefully we addressed that question. However, right, we actually introduce a new question, which is, well, first of all, okay, this question still stands, right? Can this work efficiently? Because now you have to remap it every successful steal. But furthermore, this extra fragmentation in the stack memory will adversely impact your performance and memory footprint. And so we have to think about that. But before I get there, let me talk about how we actually support TLM in practice, okay? Ideally, this is really what you want to do. Okay, so for those of you who are theoreticians, the operating system, and I think Rob actually talked about this like yesterday, right? When you translate from virtual memory to physical memory, there's this thing called page table. I'm drawing it this way because, in practice, you have page table that are basically just 4 levels. Each level, you can think of it, it's an array of linked list. So you have the top level point to the next level and so on. And then eventually, when you get to the bottom, the entry in the bottom level table tells you how to translate from your virtual address to physical address, like which physical page that particular entry actually corresponds to. So ideally, what you want to do is you have a page table that is used by all the threads when you have shared memory range. But then for each thread, the TLM region, you just have its own individual page table for that particular range of virtual address. Anybody see a problem with this?
Threads share the same address space, so.
Well, but that's precisely what TLM is trying to change, right? And this is why we have separate page table, the page table for share range and the page table for private range. Okay, well, this ideal implementation doesn't work because in real system, you have this pesky constraint that the hardware walks the page table. When you have a page fall, the hardware just go to a particular register and say, where's the root of the page table? It's not gonna do this computing of like, hey, which region does it fall under, and let me pick the corresponding page table. It just can't do that. It doesn't have the capacity because the hardware is the one that's doing that. And so basically what that means is that each thread has to have a single root page directory, both for shared and private region. So this is what we end up doing, where each thread now has its own root page directory. But then whenever you have the shared region, the bottom level is shared. But then whenever you need to basically update your root page directory, now you have to synchronize among threads, okay? And so this way, because these entries are in principle shared, so you have to keep the value up to date and consistent across all threads. And then you have to just single entry reserved for the private one. Okay, any questions so far? Okay, hopefully not. And you know, this required about 600 lines of code in the Linux kernel. All right, so that's how we implement TOMN. Now the next question, will a work stealing runtime work well if it needs to remap the stack at every successful steal? What's the system call? Okay, so if you think about work stealing, right? Actually, if your application has ample parallelism, you're not gonna steal very often because steals are basically used for load balancing. And if all the worker always have work that they already have and they're just executing that work, they're not gonna steal very frequently. So like maybe, but obviously in system work, you can't just be like using that as an argument. That's not very satisfactory. So to answer these questions, we actually have to implement the system. And we did build a system, and I apologize for the version number because this is actually really, really old work. We implement a prototype runtime system that utilizes TOMN, and we call that system SilkM. That's built based on the open source Silk 5 runtime system. And we modify the open source Linux kernel to provide support for TOMN. And as I mentioned, it's about 600 lines of code. We did not build a SilkM compiler. All the benchmarks are hand compiled. Okay, so how does it perform? Actually, it performs pretty well, right? And in fact, on some of the benchmark where the spawn overhead shows up, it actually performs better because we no longer have this heap linkage. Okay, it allows us to actually do certain things more efficiently. All right, so I should say these are benchmarks, and what the number is showing is the SilkM running time on 16 core divided by the Silk 5 running time. So if it's less than 1, that means SilkM performs better. If it's above 1, that means SilkM performs a little worse.
And Silk 5 was the one that doesn't use legacy code, is that right?
That's correct, yeah, exactly. Okay, so in practice, it seems like even though the C in front of the T infinity term is no longer constant, in practice, it works well, provided that your application has decent amount of parallelism, because you simply do not steal very often. Spacebound. Here, again, the same set of application. D is that silk depth term that I talked about in the theory. S1 is the number of pages used by the program when you run on one worker. S16 is the number of pages used by 16 workers, and then we divide that by 16 to just get an average of how many pages each worker used in the parallel execution. And as you can see, even though D is quite large, in practice, again, it's pretty small. And the reason being, again, assuming your application has decent parallelism, you're not going to steal very often, so you're not going to do this fragmentation very frequently. Okay, so to summarize, in my humble opinion, you start with a problem with a practical system implication, because we really, really want a parallel platform that provides both good bounds on time and space and interoperability with serial code. Explore the solution space guided by theory and informed by system. So the initial solution I show, it's nice, but obviously it doesn't quite work because you actually need to work with real system constraint if you're going to implement this thing. And then finally, well, I hope I convinced you that the solution provides good theoretical guarantee and is practical. And we built a prototype system to demonstrate that. Okay? All right, so yay, paper writing time. Eventually, this paper was published in PAC 2010. As I mentioned, it's really old work, but I thought it illustrates, my point pretty well, and this is why I chose this work. I will say, so Martin was saying that he found that system people always interested in the theoretical work. Honestly, that's not really my experience. Whenever I submit system paper with some kind of algorithm in it, depending on the reviewers, sometimes I can get pretty hostile reaction. And so the reason why we say eventually is because we actually tried to submit it multiple times, and then it finally got in like the third try. In previous submission, we got comments like, do we really care about stack spacebound? Or only 600 lines of code added. And I interpret that as some system person saying, your paper is not system enough. All right.
So maybe the first comment being that only do we care about the stack space bound? I mean, if the systems person doesn't care, who does?
I think the particular reviewer, so clearly he cared about interoperability, or he or she. But he or she believes that, because in the paper we also sketch out other proposal that doesn't have either the space bound or time bound. And,
I see.
yeah.
So did you do something to adapt the paper when you resubmitted, or just hope to get more sympathetic reviewers?
I mean, okay, 600 lines is 600 lines. There's nothing we can do to change that, right? I think we tried to rewrite it better, but beyond that, like the actual technical stuff, we didn't really change anything. Yeah. Okay. The race detection problem. So what is the race detection problem? Again, I'm going to be using the same model, but in this case, actually, the work applied to it doesn't matter what language you use. There are many languages that use things like spawn and sync, like TBB, hub, and arrow. It's applicable in those contexts as well. Okay, so now I'm actually going to walk through how we model the computation, but for you guys, this should be the easy stuff, right? When you execute, basically this DAG unfolds as the program execute, where when you hit a spawn, there are two outgoing edges. One goes to the spawn function, the other one goes to the continuation. And then the DAG can unfold dynamically as the program execute. And then when you hit a sync, basically you have the edges joining, okay? So in this context, what do we mean by determinacy race? Basically, we say when two logically parallel strands access the same memory location, and one of them being a write, okay? So what do I mean by logically parallel? Again, in the context of this DAG, say if I have a node here that perform write on X, another node perform write on X, is that a race? No, it's not a race, right? Because there is actually a directed path from this node to this node. So they are not logically in parallel. They are in series. So basically, when I say in series, I meant the two nodes have a path, directed path between them. On the other hand, if this node reads X, is that a race? That is a race because these two are logically in parallel. There's not a directed path between this node and this node. Okay? And typically, in the context of task parallelism, we consider this as a bug because it leads to non-deterministic program behaviors. And so we really want to be able to catch this kind of bug dynamically as you execute the program. There's a pretty long history that people actually look at this problem a lot. And I'm going to focus on the Bender et al. Because this is sort of the state-of-the-art algorithm for doing race detection when we did our work. There are some people who did practical work where they have a race detector, but they're not concerned with resource bound. So in this case, they basically built out the entire computation tree during runtime. And then whenever you detect race, you basically have to walk that computation tree to see if two things are logically in parallel. And as you can imagine, that's pretty expensive because each read and write becomes a tree traversal problem. Okay. All right. So let me describe the state of art. In this paper, they actually describe two different algorithms. SP order, which is the first asymptotically optimal sequential algorithm. It incurs constant overhead during race detection, meaning that when you run the program sequentially, it runs in big old T1 time. It also proposes a different algorithm that is a parallel algorithm. You can run it in parallel. However, if you know this, right, we know work stealing can schedule the computation in T1 over P plus T infinity time. This algorithm incurs a P overhead in front of the T infinity term. That means it needs P time higher parallelism for race detection run to get the same speed up as the baseline without race detection. But actually, that's for me not such a big problem. The bigger problem is there's no practical implementation exist. Why? Because in order to allow SP hybrid to run in parallel, they have this complicated data structure that they are maintaining and additional things that they need to do during the runtime. And just, it's so complex that nobody ever tried to implement it. Actually, I think maybe a master's student tried, but it was so buggy that, yeah, he tried. Okay, so basically, what is the race detection problem? The problem is that we really want to be able to do the following. We want to build a race detector that allows the program to execute in parallel. We want to be able to detect races efficiently in practice and in theory, meaning that we want to have an actual implementation that does that. And ideally, it would be nice if we can run it in expected T1 over P plus T infinity time, going back to the realm of constant overhead for race detection. And we want to be able to provide strong correctness guarantee, report race if and only if a race exists for a given input. Now, I will mention this is actually pretty standard in task parallel code. If you're more familiar with the p-thread model, this is not usually possible because of the large number schedule. In the realm of task parallelism, you can provide such guarantee. Okay, any questions so far? What's the DAG and logically series parallel and so on? No, okay.
So for this, there is only one DAG in an execution. There couldn't be another execution that creates a different DAG?
So for a given program, for a given input, you always have the same DAG until you encounter a determinacy race. But then by the point you're done because you found the race and you, yeah.
Okay.
But yes.
The only obligation is to report the race, not to do anything to prevent non-determinism or something.
That's correct, yeah. Think of this as a tool that the programmer used to say, hey, do I have a determinacy race in my code? But not to automatically fix it or prevent it or anything like that.
And this is a runtime thing, right? Because it's input dependent.
Yes, this tool have to actually execute the program with the set input and then tells you, hey, for this given input, do I see a race?
So basically the outcome is you can't, if you care about determinism.
You can just call it race, it's okay.
You just say that it doesn't work, that's all, right? During runtime. There is no fix. It's not like, then you go back
That's right.
to debug.
It's a testing tool. So you run the program on one input, fix all the races, run the program on another input, fix all the races, and then once you've run it on some number of inputs that makes you happy, then you're done, right? Like this is a
It's
normal
got
testing
it.
tool.
That's right, yeah. Yeah, but this guarantee is pretty important, right? Because if you run the program for a given input, it tells you there's no race. That means for that program, for that input, there's no race. It doesn't mean that, oh, there's some other schedule I didn't see that there could be a race. It just means, okay, for this given input, this program, there's no race. And if you run the program on enough input to exercise your code enough, you're pretty confident that your program does not have a race.
If your DAG depends on some randomness, can that cause a problem?
So the reason why I say this is only really applying, so yes, if you're gonna say, I'm gonna flip a coin, and if the coin return this, then execute this, otherwise exit, then yeah, that would not. However, right, in this case, I consider the coin flip as an input. Yeah. Okay, good. So hopefully we're all on the same page. Okay, so then we looked at this, we're just like, okay, let's first think about why is it challenging to parallelize SP order, right? SP order is actually a really cute algorithm. So SP order is the state-of-the-art serial algorithm that cannot run in parallel. Now let's see why does it not work in parallel. So when you talk about race detection, typically there are two components that we care about. The first component is what we call series parallel maintenance. Basically, you can think of it as a data structure that can tell us whether given two strands, whether they are logically in parallel or not, right? So if I have a SP maintenance data structure, I can say, hey, look at this node and this node. Are they logically in parallel or not? And then there's also the component of access history, basically tells us which strand accesses a given memory location. So then what you do is, during runtime, say this node writes X. Okay, you're gonna put that node into the series parallel maintenance data structure, but also remember the fact that in the access history, this node wrote X, okay? And then when the no come and read the same memory location, it's going to ask the access history, hey, did someone else write to X earlier? The access says, yes, this guy. And then you query the SP maintenance and say, hey, is this guy logically in parallel with me? If so, voila, there's a race. Okay? So these are the two main components, SP maintenance and access history. Now, so the SP order is basically an algorithm to allow you to do SP maintenance. In particular, it actually uses two data structures, but it maintains two total orders of strands, and I'm using nodes and strands sort of interchangeably, but it maintains two total orders of strands and decides the series parallel relationship by comparing the relative ordering in these two orders. Okay, I'll use an example. But basically, we have what we call the English order and the Hebrew order. So the English order, you can think of it as basically depth first, left to right traversal of your DAG, right? So here, I'm labeling all the nodes A, B, C, D, E, F, G, and so on. So the English order is effectively labeling the node in depth first, left to right traversal order, okay? You can think of it as just the serial walk of the DAG. The Hebrew order is the complementary one, where it's depth first, but right to left, okay? So in this case, the Hebrew order will be A, B, but instead of go to the left, I'm gonna go to the right first. So I'm gonna traverse right M, and then P and Q, but I can't go here yet because I haven't traversed these. So I go back up and N and O and so on and so forth. Okay? So as the DAG unfold and the program execute, basically the SP order will keep one data structure that maintains the English order of all the strings that it's seen so far, and the Hebrew order of all the strings it's seen so far. And then, as I mentioned, right, it compared the relative order of the strands to determine in those two orders to determine whether they are logically in series or in parallel. For example, say B and J. Okay, so that's B, and that's J. In look at English order, B is before J. In Hebrew order, B is also before J. So B is always before J. So we know they're in series. On the other hand, let's say G and P. Well, in this case, in the English order, G is before P, but in the Hebrew order, P is before G. So they are actually logically in parallel. That's kind of cute, right? Well, I think so. I like it a lot. Okay, so as I mentioned, 2D order use two-order maintenance data structure. So that's a typo. It should be SP order. To keep track of English and Hebrew order, at each strain execute, the SP order will perform insertion into the own data structure. At each memory access, the SP order perform a query. Okay? Now, you look at this algorithm, you're like, it doesn't seem like it's not parallelizable. It seems inherently sequential. But the problem is we run into issues when you use the own data structure during parallel execution. Okay? So let's see what's the problem. Well, with the ON data structure, basically, it assigns labels to nodes and then use labels and label to determine the order of nodes. But basically, the way you think about it at a high level is it's a two-level data structure. The top level data structure is just a balanced binary search tree. It doesn't really contain real data. It's just internal nodes. And then all the what we call groups are at the leaves. And each group is a bottom level structure. And each group can contain up to order log n nodes. Okay. And a sequential ordinate data structure, when you do queries, it's order one worst case. When you do insert, it's order one amortized. Okay. And what do I mean by amortized? Well, because from time to time, in order to maintain the good bound, you actually have to rebalance the data structure. So whenever the group gets full, after insertion, you basically have to rebuild the top level tree to rebalance it. And that might actually touch the entire data structure. And so in this case, say we insert into the bottom group, it becomes full. And now we actually have to look at this top level tree and rebalance it. Okay? And so in the case where we have the race detection algorithm, the SP order, the good news is that actually insertion and queries can be done in parallel as long as there's no rebalance, okay? Because it turns out that the race detector uses the ON data structure in a very special way, where this part I did not prepare, so I'm not explaining it well. But it uses it in a very different way, special way, such that we know whenever you insert into something, you always insert into the bottom group, but you are always going to insert into a different location. I don't want to get into the detail, but just suffice to know that insert and query can execute in parallel, okay? Now, the bad news is that whenever an insert triggers a rebalance, that basically conflicts with everything. And whenever you do rebalance, you basically can't do any insert or query. Okay, so how do we solve this problem? And this is why the SP order cannot be parallelized easily, okay? So our initial attempt is that, okay, you know, let's just design a good parallel data structure and we're gonna use a system approach. So what do I mean by that? Well, we're gonna design efficient work stealing runtime system that basically allow you to separate your rebalance workload from everything else. And when I say everything else, basically the execution of user code while you do race detection.
Go one step earlier. Why do you need to insert? So this is the thing that does two DFSs. This part.
This is the order maintenance data structure that maintain the ordering of strands
Ordering
of the nodes.
Okay, so that's not, I mean, does it change? I mean, for a specific input, there's a specific scheduling, it's fixed and it's determined, right? Why do you need to insert the lead? So and then you said you do a Hebrew thing and an English thing, and then you're done. You can answer all questions, right?
So there's no deletion. There's only insert and query.
Okay.
And yes, okay, so this is the part that's not clear.
Wait, can you wait until you finish the execution and then do the Hebrew and English and then do all the checks? Or you need to do it online when you get an execution in the middle? You have to find out the race.
So we prefer to do it online
And why?
for two reasons. Well, one is that actually in the example that I cited, those are like, you know, I think prior to those work, people were trying to do offline where you will have program traces, you store all the traces, and that turns out to be really expensive. And people want to do this online so that you don't have to store everything and then process it. So that's the first point. The second point is that once you encounter the first race, technically the rest of the DAG is like you are no longer deterministic, right? So the rest of the DAG that you're exploring, it's not clear that it's correct.
Sure, but any DAG that you will continue, you will see the race.
I mean,
Also,
sure. So
do
maybe,
you really have to say, maybe we can take this offline.
okay. But like, did you have a question about the data
You
structure?
really have to save everything in memory in order to decide. I mean, you could do the DFS while you're working.
Well, so, right, exactly. We are doing this online, right? As we're executing the program, we are maintaining this data structure that keeps track of the two orders.
Okay, we can take it.
Okay, sorry, maybe I didn't understand what you're asking. Where am I? Okay, yeah, the bad news is rebalance conflict with everything. So while rebalance is going on, you just can't do anything. And so our first initial attempt is that we're gonna design efficient work stealing runtime, right? We're gonna separate the rebalance from everything else. And then we're gonna coordinate the processor to work on rebalance. So, you know, when the user code is executing, it's going to do like things like insertion and query into the data structure. And we call that the core DAG, which is the core user code, but just with race detection turned on. But then maybe insert triggers or rebalance. Okay, now you need to rebalance. So we say, okay, let's just stop doing the core computation. And then we're gonna do all the rebalance. So there are no insert and query. Do the rebalance in parallel. And then whenever we finish rebalance, we go back and continue race detection, okay? But of course, rebalances are large, and we want to parallelize the rebalances. And so, you know, this include like designing the runtime that does this, and also designing a good ON data structure that allow you to do parallel rebalance. Okay, but before we implement the system, we decide we're going to do a backup envelope calculation. Assuming we can build this runtime system that allow you to switch efficiently between the two, every switch incurs constant overhead, what kind of bound do we get? And what kind of bound can we get on the parallel rebalance? Well, the core part, always good, right? For the core computation, basically the bound is the same without the rebalance, assuming that the switching back and forth does not incur too much overhead. You can still do this in T1 over P plus T infinity expected time, which is what we want. Now, what's the rebalance part? Okay, we designed the parallel rebalance, ON data structure parallel rebalance. Assuming we have n total insert, then the total rebalance work, the amount of work incurred, is order n. The span, which is the critical path in the DAG for the rebalance work, that incur log n time, order log n time. And basically, this is the best you can hope for a parallel data structure. Okay, now here's the issue though. Assuming you have k rebalances, then your expected time for running the rebalance in parallel is now n over p plus k times log n. Okay, but if you have n nodes in your order maintenance data structure, then because each your group is order log n size, you could have k equal to order n divided by log n, number of rebalance. And so when you plug this in, well, okay, the log n cancels out, and now you have n, now you get order n. But this time, if you're gonna incur order n time, this is basically the same as sequential execution, even though you parallelize your rebalance, right? The fact that you have so many rebalance, you end up getting the same execution time as order T1, even though you execute things in parallel. So that's bad. So then we're like, can we reduce the number of rebalances? So yes, the answer is yes. We decided that we're going to do proactive splitting, which is counterintuitive. So whenever rebalance gets triggered, right, it's because some group became full when you try to insert into that group. So we can do proactive splitting. What that means is that when we trigger a rebalance, we don't just rebalance the tree for the group that's full, but rather we're going to look at all the group that's almost full. And then we're going to basically split all the group that's almost full and then rebalance the tree. Okay, so basically you can think of it as we're batching the group splitting so that every time we do a rebalance, we're doing the rebalance for more groups. So with this, then what that means is that after a single rebalance, all the group at the bottom level have room for more insertion. Okay, and this actually depends on how we use the order maintenance data structure, because we use it in a very specialized way. What that means is that we know, because all the group has rooms, now we can execute for at least omega log n amount of time before some group become full again. And so what that means is that expected number of rebalances is the parallel execution running time divided by log n. And when you plug that in, well, then the expected time in rebalance goes back to T1 over P plus T infinity, which is what we want. Okay, I know I'm running low on time, so I'm going to wrap up really quickly because I know I'm like the last thing between you and lunch. So again, in system consideration, we want to build an efficient ON data structure. We want to build a work stealing schedule that allows the worker to switch between the two types of work efficiently. This is what we end up building. We have to build an ON data structure that supports insert query and parallel rebalance with proactive group splitting. We have to have a specialized work stealing runtime that allows the worker to switch between user code and ON parallel rebalance code. We need to actually have a race detector that utilizes the special scheduler and that basically implement the series parallel maintenance, the access history, and then we also need compiler instrumentation so we can actually compile the program to do race detection. So basically you need an end-to-end system in this case. Well, okay. I am running low on time, so I'm just gonna wrap this up. It scales pretty well. And the reason why we want parallel race detection, so this is our system. You can see it can be parallelized. So when you run on more number of core, the running time of program decreases. These are two other systems that implement the sound algorithm, but they can only run sequentially. And as you can see, the full race detection incurs a lot of overhead, and this is why you should parallelize it, okay? And yesterday in Rob's talk, he said we don't get out of bed for less than factor of 2. This is factor of p, okay? All right, so I promise we have other number, but I'm just not gonna go through them because I'm out of time. Again, just repeat my point. Interesting system plus algorithms research is start with a problem with practical system implication because we really want a race detector that can run in parallel. And we expose a solution space guided by theory and informed by system. Before you build the system, you can do some back of the envelope calculation, assuming your system is based on some theory, and that can actually save you a lot of work. And then finally, in this case, well, we actually needed to build end-to-end prototype system to demonstrate that. All right. And just to acknowledge, these are my class. And when I say we, I really mean the poor grad student who has to build everything. All right. Okay, so that's the end of my talk, and I will thank you for your attention.
So how many lines of code in the second one?
Oh man, I don't know. How many lines do you think?
A lot.
A lot. So the thing is, right, this project when we started, the PhD student already has one project under his belt. It's like this system, work ceiling runtime system that allow you to batch operations for concurrent data structure. But then we're like,
it was going to be easy, but then.
we thought we could reuse that system and have this be done easily. It turns out not to be the case, bottom line, yeah. Okay.
Thanks for hearing. I know we're headed to lunch. I just want 30 seconds. Simon's programs traditionally start with a boot camp. A boot camp means sort of an introduction for people that don't have it. So the purpose of this week is to try to give a flavor for what algorithmic research and systems means to people that didn't have that background. So that was the point. All right, enjoy your lunch.